Okay, level 2 physics. Let's do some radiation. Just saw an alpha particle pass by there. Then we're going to be introduced to the high-speed beta particle. Just race past on the screen. And finally, the high-speed gamma radiation. Not a particle. So this is a radioactive substance here. It's all emitting particles. All the research of Marie Curie and Antoine-Henri Becquerel. We're going to talk about radiation today, and in particular alpha, beta, and gamma radiation. So, in 1896, Becquerel accidentally discovered that the uranium crystals emitted an invisible radiation when exposed to enclosed photographic plates. So he had his plate, his photographic film, he accidentally put the uranium salt on top, and then something magical happened. Okay, there was something in the salts that affected the photographic film. So there's his notes, and you can clearly see from his notes that it was unexpected. He didn't think it was going to happen, but the salts did something to his photographic plate. So in between 1867 and 1934, probably one of the greatest scientists in humanity, Marie Curie discovered that thorium was a radioactive element. In fact, in 1898, Marie and her husband, Pierre, discovered polonium and radium, two new radioactive elements. Radium was interesting because it glowed green. So in the 1890s and early 1900s, a lot of French women especially wore jewelry that glowed in the dark from the radium. Unfortunately, one of the side effects is they ended up getting throat cancer from the radiation. There you go. Vanity. So, the Kiwi, Ernest Rutherford, who you may have seen on all the $50 notes you all have in your pockets, found three types of radiation were emitted from a radium source, and they could be separated using a magnetic field. So what he did is he put his radium source into a lead box. There we go. He had a lead slit, and then a photofilm was used to detect the radiation. So when the radiation hit the photofilm, just with Becquerel's accident, what happened was you could actually see the radiation hitting. So lead box, the particles will then pass through a magnetic field acting inwards, and they were deflected. Well, at least two of the three types were deflected, and the final one just shot through. So he surmised that one of the particles, of these three particles, was positive, and this is known as the alpha particle. One was negative, this is known as the beta particle, and it got deflected as well. And the gamma ray was not deflected at all, it went straight through the magnetic field and hit the photofilm and was detected. So here is an atomic symbol, which for those who are taking chemistry you should be familiar with. So the chemical symbol in this example is the giant X. The proton number, or number of protons in the nucleus, which defines what the element is the Z value here, the lower number, and the top number is known as the nucleon number, and that is the number of protons plus the number of neutrons in the nucleus of that atom. So alpha particles are helium nuclei. Okay, they have two protons, two neutrons, therefore their atomic number is 2 and the nucleon number is 4. So they usually travel at about 10% the speed of light, and they have energy of around 5 mega electron volts. Beta particles, on the other hand, are high-speed electrons. There we go, just passing through there. So they have -1 as their atomic number, or nuclear number, and 0 for their nucleon number because there's no protons or no neutrons. And they go pretty fast, about 0.99 the speed of light. Okay, can't go 100% the speed of light, relativity, because then they'd weigh the mass of the universe, and that could not happen, of course. And finally, we have gamma rays, and these can be seen as energetic photons. So there we go there. So it has no atomic mass and no nucleon number, because it doesn't contain any protons or neutrons. That travels at the speed of light because it has no mass, it can, and it has a wavelength of around 10 to the negative 11 meters to 10 to the negative 13 meters. So quite a short wavelength, and because it's such a short wavelength, it has quite a lot of energy packing. So if you have some gamma rays going into your DNA, you might be in a little bit of trouble. Right, so radioactive atoms have too many neutrons, makes them the nucleus quite unstable, and possibly also too many protons. So it wants to get stable, it wants to get rid of these, wants to get rid of the neutrons, also wants to get rid of the protons. So usually because it involves having too many neutrons or protons, the very heavier atoms of the periodic table, like thorium and uranium, polonium, are usually radioactive. Okay, because they're just too big in the nucleus, there's too much going on, too much jamming. They want to become stable by breaking up. Okay, so if an atom becomes radioactive, if its neutron-proton ratio is outside of the idea of a band of stability. So all elements with a number of protons greater than 83, i.e. those past bismuth on the periodic table, are naturally radioactive. An unstable nucleus can emit radioactive particles in order to then gain stability. So it can lose protons, can lose electrons, or can lose gamma radiation to become stable, usually a combination of those. So I'm just going to now go through the different ways radioactive atoms can decompose to become stable. And the first one is the beta particle production. The second one, of course, is alpha particle production, and finally gamma ray emission. Usually you get gamma ray emission with the other two as well, because remember it's just a loss of energy. Okay, so if we plot the number of neutrons against the number of protons in an atom, we get a nice line here which is blue, which is all the stable nucleotides. Okay, so all the stable nucleotides lie upon that blue line. Okay, and the stability line follows when n equals z. The n equals z line up to when a number of protons equals about 16. Okay, unstable nuclei lie either side of the stability line. The exact position on that this plot of this graph determines how it decomposes to become stable. Okay, so there we go. That blue line is the stability line, and alpha decay only occurs when the number of protons number of protons Z is greater than 83, greater than bismuth. Okay, so we just color that in there. So all those atoms in which the ratio of neutrons and protons falls within the purple region decay through alpha emission. Okay, that's what that's saying. Whereas if we look again with that stable line, for those in the blue region, when you look at the number of protons and number of neutrons in the atom, then it's going to be falling with becoming stable by emitting a beta particle. And finally, you can get stability line, beta plus emission or electron capture occurs in the purple region. Okay, so that's when the actual nucleus either gets rid of a positron or actually takes an electron, and that's how it becomes stable. Okay, so beta plus or electron capture occurs in the... Okay, so let's look at alpha decay examples here. So here we have a atom, an unstable atom. It undergoes alpha decay to release a alpha particle, which is equivalent to a helium atom. Okay, so it's going to lose 4 nucleons, 2 neutrons and 2 protons, and also it's going to then emit or form a atom which has lost these 4 nucleons, and of course energy. So here's an example here. So you've got your atom, it releases energy and also releases a alpha particle to become a new atom. So I'm just going to illustrate here by an example. So here we have 226 radium. Okay, so it undergoes alpha decay to become 222 radon plus the alpha particle plus energy. So it becomes more stable by releasing the alpha particle. And the energy comes from the binding energy of the nucleons in the atom that's now decomposed through E equals mc squared. Okay, so beta decay. So in beta decay, a neutron in the nucleus turns into a proton, an electron, and an antineutrino. The nucleus now has one more proton than it started with. So here we go. Here's a atom. It undergoes the beta decay. It emits a antineutrino and a electron. So here's an example here. So you've got 14 carbon. It is now turned into 14 nitrogen. It has released a beta particle and an antineutrino. I'll be honest with you, for level 2 you don't really need to worry about the antineutrinos, but the antineutrino was important because there was slightly a mass imbalance between the two products. So physicists had to find out what that was, and they discovered the antineutrino, which is essentially the additional mass that was converted in the beta decay. Okay, so during a beta plus decay, a proton in the atom's nucleus turns into a neutron, a positron, and a neutrino. So another example there, 10 carbon going to 10 boron, emitting this time a positron plus a antineutrino. Or this time, sorry, a neutrino. Okay, so this is the uranium-238 decay chain. So what happens is you have the very unstable uranium-238, and it slowly, over time, becomes more stable. Okay, goes from, this is all through alpha emission, beta emission, and gamma emission. So it's just an animation there illustrating how it slowly goes from uranium-238 through a series of intermediate atoms and through different mechanisms to finally become the stable lead-82. Okay, so this is just all the half-lives. Okay, so a half-life is essentially the amount of time it takes for half the radioisotope to mass to disappear. So that means if you have 100 grams of uranium-238, it takes 4.5 billion years until you're left with 50 grams. So you notice there you've got quite a number of different half-lives. By and large, the shorter the half-life, the less stable the radioactive atom is. So for example, polonium, pretty unstable, 0.002 seconds. Okay, and you notice it takes a very long time in order to go from uranium-238, which is radioactive and unstable, all the way down to the stable isotope of lead-206. And this is a way you can actually date rocks, especially. Okay, so in terms of the properties of alpha, beta, and gamma particles, so your average alpha particle is quite slow moving, doesn't have much energy, so it can be stopped by a paper sheet. Whereas something like a high-speed beta particle, which is traveling 0.99 the speeds of light, takes a bit more slowing down. So it takes about 2 millimeters of aluminium to slow down and stop a beta particle. And finally, the high-speed gamma particles, a majority are stopped by a few centimeters of lead, but some still get through. So this is one of the reasons why, say, in X-rays departments, usually the person behind the screen is covered well, the screen is actually made or lined with lead, even the glass, lead glass. Reason why is this person's working with radioactive isotopes for the whole his whole working day or whole working week, whereas you're only getting one off X-ray, so he needs to be protected from the radiation. Okay, so just to summarize the range of particles in the air. So an alpha radiation has a range of about a few centimeters in air because the particles are charged and so they interact with the oxygen in the atmosphere, and they're relatively big and slow and fat, so they interact with the air molecules and produce about 200,000 ion pairs per centimeters of travel, and also it doesn't take much to slow it down. Okay, slow moving and quite big. Whereas beta particles, they have a range of about a few meters in air because they still interact with the air, but because they're so fast, it takes a lot more to slow them down. And gamma radiation has an unlimited range in air, so you don't really like that. Okay, and finally, just to complete, neutron radiation, which we won't really go into in level 2 physics, has a similar range to gamma radiation because they travel pretty fast as well. So that's pretty much a summary of alpha, beta, and gamma radiation. So our next topic will be investigating the famous experiment by New Zealander Rutherford and how he elucidated the structure of the nucleus.